or any clarifications about the examples that I made in previous lecture? Remember that we have 4 different circuits. Some of them are having advantages and disadvantages in the same time. And I explained step by step how to calculate all the values that is required for any of these circuits. Now, going back to the BJTs, that's, the transistors that are used in active region. With a bit of noise, from now on. Somebody's cutting, the lawn. And in the active region, remember that we are using, the transistor that is in the active region. Ideally, in the active region, we are looking to place the transistor closer or in the middle of the load line, and or anywhere around the middle of the load line. It's a good calculation or a good design of using the transistor in the active region. Another basic application for a transistor is in digital logics. In digital logics, we'll discuss more details next term. We have a course in digital logics. The transistor is placed in the saturation region, which is the left side of the y-axis, or in cut-off region, which is the region below the x-axis. Means that we have to push the transistor between the two limits. Means that we have to push the transistor to the IC or the VCE. If the transistor is not used in analog applications or as a switch, the transistor may be turned on and may be turned off. And those are the two equivalent circuits that may be used in order to design or to see, the basic functionality of a transistor as a switch. You notice that if the transistor is in cut-off, remember that in the cut-off region, the IB or the base current is equal to 0. Means that if the base current is 0, the IC becomes 0, knowing the relationship between the IB and the IC through the beta of the transistor, and the transistor, it will act as an off switch. And you notice that in this equivalent circuit, you notice that on the right side we have the equivalent circuit that has the voltage source, the resistance RC, and the switching off position. Means that if there is no current applied to the base, the transistor, it will act as, or it will, or looks like an open circuit. If there is enough current applied to the base, and I will show you how to calculate that current, the transistor may go in saturation. Means that the voltage across the base, the collector emitter, is 0, means that the switch is closed. Means that the transistor, it will act as a closed. Yeah. Yes, please. Any questions, please? Okay, means that the switch, the transistor, it will act as a closed switch with the voltage between the collector and the emitter as being equal to 0. Again, that's the voltage ideal in our calculation, but remember that the real value of this voltage emitter in saturation is not zero, it's close to zero, as zero point 0.1 to 0.4 volts, which makes a very good approximation to look at the transistor as the as a switch that is closed in saturation. Now, when the transistor is used as a switch and applying, the proper bias, the cut off or the switch off, or the saturation when the transistor, it will act as a switch on. Now, there is no calculations or no limits in finding the IB or choosing the IB as zero. Just disconnect any voltages or any currents that is applied to the base of the transistor, which makes the IB zero, means that the easiest way to determine the or to push the transistor or to put the transistor in the off state, or the transistor is switched off, is applying a zero voltage or not having any current to the base of the transistor. The only calculations or the only limits and the only precaution is to turn on the transistor in the saturation, means that we have to push the transistor on the maximum current that can flow through the circuit, through the transistor, in the saturation mode, or when the transistor is in on state. Now, the only calculations or the only precautions that we have to assure that in saturation, and remember that we have the resistance RC, which is connected to the voltage source VCC. In order to make sure that the transistor is in saturation mode, we have to make sure that the IB, or the base current, is greater, I will not say equal, but just a bit above the saturation current, the IC set over the beta DC. Now, on the right side of this, these equations are showing, a basic circuit that uses a transistor in the switching mode. You notice that once we are applying the voltage or enough voltage to the base, the current is applied to the base, means that I can turn the transistor on and off. You notice that, and that's another good way of showing the beta DC. I mentioned that is the same thing with the HFE. HFE is called the transfer function, or the amplification, which is the same thing with the beta DC, but in specs sometimes you will see this notation, which has the same meaning with the beta DC of the transistor, and is given as one of the lowest, let's say 125 or 100 or 50, any values that is a good amplification or a good gain in current. In this example is given as the HFE as 125, as a voltage is applied to the base. You notice that the voltage is switched on and off, means that the transistor, it will act as a switch and will be turned on and off based on the voltage applied to the base. On the output, you notice that the output has the opposite voltages with the input. Suppose that for this interval, you notice that the voltage is equal to 0, which makes the VC, or the voltage at the collector, as the maximum voltage because the transistor is in off state, means that there is no current that flows through the transistor, means that the voltage at the collector is equally the maximum voltage, which is the 5 volts supplied voltage. When a voltage like 5 volts is applied to the base, there is a current that is supplied to the base of the transistor. The transistor is turned on, means that the collector emitter voltage, that's the collector emitter voltage, let's say it's almost zero, means that the VC, or the potential at the collector, is equal to zero. And vice versa, when the on the lower side of the lowest voltage or zero voltage is applied again on the base, transistor is turned off, and the VC becomes the maximum voltage or the supplied voltage, 5 volts. Now, what did you notice? What's the most important part of this diagram? I'm applying zero, but I'm getting the VC, or the output voltage, as the maximum voltage, and vice versa. Once I'm applying a large voltage, or 5 volts in this case, I will get the zero voltage. You notice that those two signals are opposite to each other, means that I'm applying 0 volts or I'm applying no voltage. I'm getting the highest voltage, which is the VCC. I'm applying a voltage on the base. I'm getting 0 voltage. Transistor, it's working as a switch, but has that inverting function. You notice that again, the output is 180 degrees out of phase with the input. Means that I'm trying just to have a transition between the electronic devices or discourse and the digital logics. I will just introduce the Boolean algebra that you will study in digital logics. But again, it's just a transition. I'm just giving some ideas what we'll discuss in details in next term. Now, this diagram is not affected for a low frequency. Remember that we talk about the specs of a transistor, and I mentioned that time the maximum frequency that can be applied on the transistor. In top of that, I talk about the capacitance between the base and the emitter. Always, the junctions, base emitter, base collector has a small capacitance. Those small capacitance, it will affect the shape of the output voltage in high frequencies. In low frequencies are not affected because this capacitance is very small. But in high frequencies, or that's actually the limitation for the transistors when it's used as a switch in high frequencies. For an idea about the switching times, now there are two switching time. Is when the transistor is turned on, means that I'm applying the voltage on the transistor, means that that's the input voltage. Now we are seeing an effect on the output voltage, means that from the time that I'm applying the input voltage and the time when I'm seeing actually the effect on the output requires a certain amount of time. Again, we will not see those distorted waveforms for low frequencies, but on the high frequency we may see a distortion on the output voltage. You notice that the response of the transistor for a step up voltage, as in this diagram, that's a step up is a rectangular waveform, which will have rectangular waveform on the output. at large frequencies, this output voltage, it will be distorted due to the capacitance, due to the amount of time that is required actually for the transistor to respond to a fast change on the input voltage. Now we have, two parameters that it will affect the rising time or the turn on time. We have, the first step, which is about, 10%, which is defined as the TD. That's, the delay time that is due to the capacitance and is due to the response of the transistor. That's why you may have, the another classification for the transistor is in terms of the applications. The applications of the transistor for the analog circuits or the analog applications, and the transistor that are made for a digital application or digital logics. The TD, again, it's just, the amount of time that is required for the transistor to supply enough current to have, the electrons that flows from the emitter to the collector, and in top of that we have to add the capacitance between the base and the emitter and the base and the collector. From 10% to 90%, those are, the calculations or, the limits between 10% and 90% most of the time in calculations. We have, the rising time. That's, the highest rate in changing the output voltage. And to determine the T on, or the rising time, which is, again, it's the Miller effect or the Miller delay, sometimes is called, which has the two parameters in it. The two values of the TR, TD are given in the specs, means that we can determine the limits, or we can determine actually the shape of the waveform that is expected when the transistor is turned on. Once it's turned on, or the transistor is reaching the maximum voltage, it will stays on with a maximum value for the current, but the same way or the same observation occurs when the transistor is turned off. You notice that, again, when the transistor is turned off, or the signal is removed, or the voltage is removed from the base. Remember that we have that storage, and the storage effect means that the capacitance, it will store a small amount of energy, and the output voltage will not be a step down voltage, it will be a small decrease, exponential decrease in voltage at the beginning, and after that it's pretty linear, and another small exponential decrease at the end of the output voltage, or the end of the cycle. The other two parameters, when is the fall time, or the turn off, or the turn off time, is the TS, which is the storage time. Again, that's based on the capacitance that is between the two junctions, and the falling time, which is the TF. Now, we are not using, too much in analog logic. We are not using, too much those rising time and falling time, or turn on, or T on, and the T off in this course. But we'll discuss, and we'll have, some other, details, and we'll have, some other limitations that are based on these two times, the turn on or the turn off time. Now, a basic application And I told you that I'm trying, to make a bridge between this course and the digital logics, which is next term course, in simply, having an inverter. Remember that in digital logics, we don't have, any intermediate values. We have, just two values. If I'll make, an observation, and you notice that I use, the 5 volts. 5 volts and 0 volts is used intensively in digital logics, in special in the TTL technology. Or TTL stands for transistor logic. Again, we'll discuss details about, the CMOS technology. We'll discuss details about the TTL technology. But at this point, you notice that I'm applying a signal, or I'm applying a voltage, or I'm turning on the transistor, and I will say that that's the one logic, and I'll put, one logic aside. When the transistor is turned off, I will label that as 0 logic, or 0L. That's, L at this point, just to emphasize that we don't have, any intermediate values between the 0 or a large current and one logic as being equal with, let's say, 5 volts at this point. 0 logic, which is equivalent, which is 0 with 0 volts in digital logic, and I mentioned that that's, in TTL. Now, you notice that the easiest way, or the simplest way to determine or to visualize actually the transistor as a switch, using a function generator, that it will have, a square waveform, which is actually visualized by using an LED. Remember that those two arrows pointed up, that's a light emitting diode. We'll discuss about the LEDs, a bit later, close to the end of the course, as some other applications of the diodes. In this way, actually, we can visualize without taking any measurements that when the transistor is on, the LED, the LED, it will light up, and vice versa. Now, let's have a look on how this circuit works. Suppose that I'm applying, sorry, that's not the I logic. I said that it's one logic. I'll put it in this way. Means that I'm applying a voltage. I'm applying 5 volts. I'm applying, one logic. And what is going to happen? I'm supplying a current to the base, applying a current to the base. The voltage between the collector and the emitter is equal to 0, means that the transistor, it will act as a closed switch, means that the LED is on. Okay, now suppose that I'm applying a 0 logic. What means 0 logic? 0 volts means that there is no voltage, or there is no current applied on the base. If there is no current applied to the base, the LED will be in off state. But again, suppose that I'm not having an LED to visualize or to see, the presence of the current that flows through the transistor. Suppose that I'm removing, the LED, and now let's try to clean up a little bit. Sorry, this one. Now let's try to clean up a little bit, and I was saying I'm adding, the output of this circuit. Remember that that's, the output, or the V out of the circuit. Okay, again, I'm going back, to the introduction to digital logics. I'm applying, the 0 volts or the 0 logic. The output, it will be one logic, or the voltage is maximum. Now, in order to see actually the transition, I will have, the logic table. Now, let's see how that works. Suppose that on the top, I'll make, the input, and on the bottom, I'll see, the effect, which is actually, is the output of the circuit. And I mentioned that I'm applying a zero logic. I'll put, a zero on the top, the effect on the output. If there is no voltage, again, there is no current that flows through the transistor, means that the output, which is the same thing with the VC. Remember that. The VC or the Vout, that's, the output of the circuit. Means that the output of the circuit or the VC, it's at the maximum, and I'm making the assumption that, the VC is equally the 5 volts. 5 volts, I mentioned that is one logic, means that if I'm applying 0 on the input, I'm getting 1 on the output. Remember that it has, it will act as an inverter. What means an inverter? The output has 180 degrees out of phase with the input. Again, 0 volts on the input, it will have 5 volts on the output. That's an inverter or an inverse function. Now, suppose that I'm applying one logic on the input. If the input is one logic, means that I'm saturating the transistor, the voltage between the collector and emitter is 0, means that the output becomes 0. Here you go. Now, I'll make, another table, and I will extend this table. And I'm looking actually to make, a circuit, or what we have to make, what we have to change in the circuit to have, the same, or the signal in having, the same phase. What that means, suppose that I'm applying 0 logic on the input, I would like to have, the 0 logic on the output. At this point, I will make, the diagram or the symbol for a not. Let's see if I can do it a bit better. It's the not function, and looks like a triangle with a circle at the end. Means that has a single output and has a single input, a single output. That's a not function. Now, an inverter has the same, or has, the equivalent in digital logic as a not, I will say that, gate. Okay. Now, again, what this gate does, because we'll introduce the Boolean algebra, we'll have, the basic circuits, and or gates, NOR gates, and again, we'll discuss, the other details in digital logics. But at this point, you notice that that circle, it's showing you that the output has an 180 degrees out of phase with the input. And we can see, from the digital table that the output is in opposite with the input. But suppose that I'm having, 2 circuits connected in series, identical circuits. Means that I'm having, the circuit, the initial circuit, and I'm adding, another circuit. Suppose that, again, I'm having, the first circuit, I'm connecting the collector of the emitter to the base of another circuit. That's, on the base of the other circuit. What is the equivalent of this circuit? You notice that I'm actually switching the phase shift twice, means that I'm applying 0 on the input, I'm getting 0 on the output. Means that having two NOT gates in series, it will cancel the phase shift between the input and the output. Means that if I'm going back to the table, suppose that I'm applying 0 voltage on the input, I'm getting 0 voltage on the output. Once I'm applying the 1 voltage or 1 logic on the input, I will get the 1 logic on the output. In this way, by choosing two identical circuits, connecting the output of the first circuit of the first transistor to the base of the second transistor, actually I'm changing again the phase shift by 180 degrees, means that the output of the two transistors connected in series, it will follow the input signal that is applied to it. Now, just a short introduction how we can combine those transistors and the gates in order to obtain different functions on the circuit. Now you notice that I'm having just a single input for this circuit. I may need to have the other inputs, and now I will end up having another symbol for an AND gate. Here you go. Now you notice that is not the triangle shape, is like half of the circle, and again having that negation or that inverting function, that's the circle. But again, it's just an introduction. I'm just showing some applications that uses integrated uses transistor as a switch and have integrated circuits that are specialized for different functions that it's used in digital logics. Okay, I'm not going about this introduction or this basic terminology or basic topic that we are using the transistor as a switch. All the other details that we'll discuss next term in digital logics, it will be given at the other course. Any questions, comments, concerns, please? I know that's a bit shorter lecture. Yeah, I'm trying to compensate with some other lectures that I was going in overtime in your break. That's why I'm trying to make to compensate some lectures that are a bit longer than the usual time. Any questions, comments, concerns, please? Remind you once again about the assignment 2. Due date is on Monday at the beginning of the lab. Have a nice weekend, guys. Thank you.